we present dense RepPoints, representing visual objects with dense point sets. Current visual perception system usually adopts a multi-stage RCN pipeline, where it first predefines a set of rectangular anchor boxes. Then the region proposal network refines those anchors to generate bounding box proposals. Next, RepPoint is used to extract the bounding box proposal feature and use it for subsequent visual perception tasks, such as object detection, instance segmentation, or human pose estimation. In the whole pipeline, bounding box serve as the intermediate representation of the object. Using bounding box representation has many benefits. It's convenient to annotate, and it's easy to extract the feature using convolutional neural network. However, it has some limitations. First, it corresponds to coarse feature extraction. As shown in the image, many feature sampling points were distributed at background regions, where it does not have rich semantic meaning. Also, it's unable to represent irregular objects like rows. Different from bounding box representation, RepPoint is a pioneer work to use a set of adaptive representative points as intermediate representation in object detection system. Those representative points can both use as flexible geometric 2D representation and semantically aligned feature extraction. And RepPoint achieves state-of-the-art performance in object detection tasks. In this work, we would like to extend and densify the representative points to enable dense visual perception tasks such as instance segmentation. Two common representations for object segments are contour and foreground mask. Most of the state-of-the-art instance segmentation methods use foreground mask to represent objects, and is usually achieved by using RCN framework, where it first detects rectangular regions of instance and perform pixel-wise verification within the rectangular regions to generate a grid mask. Another representation is object contour, which was popularized by the SLAKE framework and have been widely used in earlier age. Specifically, it defines an initial contour and iteratively deforms that contour by minimizing energy function defined with no-never image features, such as image intensity or gradient. However, this approach tends to find a local minimum in the iteration. Recently, there are also some learning-based methods trying to represent object as contour. It uses a neural network to directly regress the coordinate of the object contour from the image feature. But usually, this approach does not perform as good as the methods based on foreground mask. In fact, both contour and foreground mask can be represented using a set of points through different sampling strategy. The contour can be represented as points sampling along the object boundary, and the foreground mask can be represented as a grid of points covering the object scope. Each point in the grid has additional foreground probability. So both contour and foreground mask can be represented using a dense set of representative points, and we denoted it as dense RepPoints. Each point in the point set has a 2D location and the optional foreground probability. Both contour and grid mask has their own benefits in presenting object segments. Contour is a more concise and intuitive representation, but it cannot handle complex objects with holes. Grid mask is a more detailed representation, but is costly in computation and memory because it needs to illuminate every pixel in the image. To combine the merits of both contour and grid mask, we propose a new sampling strategy for foreground mask, which we denote as boundary sampling or distance transform sampling. Specifically, it samples adaptive points near object boundary to represent the objects, and each point has a foreground probability. So this sampling strategy is as efficient as contour sampling because the computation will distribute around object boundary regions, and is as accurate as grid sampling, since we have an additional foreground probability for each point. Next, we describe how we learned these RepPoints. We will first talk about how to learn point set coordinates. Next, we present how to learn per point foreground probability. Finally, we show how to learn instance class from the point set. To learn the dense RepPoints coordinates, we first sample points from ground truth object notation. For contour representation, we sample points along object contour. For grid mask representation, we sample grid point from object region. And for boundary mask representation, we sample point near object boundary using the truncated distance transform. The points near object boundary will have a higher probability to be sampled, and the points far away from object boundary will not be sampled. After we sample the ground truth points, we optimize the point set loss between the predicted points and the sampled points. The predicted points are initialized from object center, and we predicted the per point offset to generate the refined points. We use chamfer distance to supervise the regressed point sets. Different from bounding box regression, this RepPoints regression has more degree of freedom. To learn the per point foreground probability, we use position-sensitive map similar to RFC and tensor mask. To classify the instance category from the point set, we concatenate all the point features. However, processing a large set of features is computational and memory costly. So we divide the points into different groups and perform group pooling over each group to generate a set of grouped features. Then we concatenate the group features and use it to predict the instance class. This will reduce the computation to constant time. Next, we describe how we can infer object segments from dense RepPoints. To infer the contour, we compute the concave hole of the predicted representative points. To infer foreground mask from grid points, we perform bilinear interpolation to generate foreground mask. This is also the commonly used image resize operation. To infer foreground mask from boundary points, we perform non-grid interpretation over the unstructured representative point sets. Specifically, we first use Delaunay triangulation to triangulate the image space using the representative points. Then for each pixel, it should be fall in a triangle defined by 3 representative points. We use barocentric interpretation in the triangle to obtain the foreground probability for that pixel. In this way, we can generate foreground mask. We visualize the per point prediction and infer the foreground mask in the bottom image. The darker points are predicted to be background region, and the brighter points are predicted to be foreground region. Next, we visualize the land points in the first row of this image. We observe that land points are mainly distributed around object boundary, and we visualize the inferred foreground mask in the second row of the image. Next, we show ablation study and the state-of-the-art comparison. For ablation study, we first compare different representations of object segments. The contour representation is effective when we only use a small number of points, while the grid mask representation achieves better performance at a large number of points. Our proposed boundary mask representation compares the merits of both contour and grid mask, and it achieves best performance across different number of points. Next, we show the results on different number of points. We observe that the performance will increase consistently with the number of points. This demonstrates the importance of densified points. Next, we compare our methods with other approach. We achieve the state-of-the-art performance on both instance segmentation and object detection. On instance segmentation task, we achieve a 1.3 AP improvement over the previous best results. On object detections, we achieve a 1.2 AP improvement over the previous state-of-the-art methods. Finally, we show the insights on some potential future work. The first possible direction is to use unstructured data representation for other 2D visual tasks, especially for high-definition media. The second possible direction is to learn the key points or correspondence in an unsupervised fashion from videos through data augmentation or from simulated data. In our approach, we link representative points with same index across different objects. We observe that the link lies parallel. This demonstrates the potential to learn dense correspondence. Another possible direction is to use our approach for box-free visual perception tasks, such as key points estimation, video tracking, and etc. Thanks for listening.